That's right.
Okay, let's get started. So as far as your exam, if you want to see your result on the multiple choice, you can come after class. I can just show you what you got, how many you got right on the multiple choice. I may or may not have the exams for you Wednesday. For sure Monday, maybe Wednesday. I can't guarantee that. Just super busy. But like I said, stop by, see your multiple choice results after class. Okay, so let's look at a different one first. So this one had the lowest success. So here's another sequence, Bn, 2n minus 7 over 12n plus 4. So this is really, basically, it's like a precalculus problem. So we can think of this like as a rational function. F of x equals 2x minus 7, 12x plus 4. So in your precalculus, advanced algebra career, you knew that these were rational functions, and so we're looking for what happens as x gets really, really big. Because whatever happens to the function f when x gets really, really big is going to be the exact same thing that happens to the sequence when n gets really, really big. Okay? We saw that picture last time. So if you have, some sequence, who knows that does this, the function will just be all the continuous points. And so whatever the function does for large values of x will be the exact same place that the sequence goes for large values of n. So how do we do this? So we look at the leading term, right? So when x gets really, really big, this is going to dwarf -7, and this is going to dwarf 4. So it's -7 and 4 just kind of disappear for large x. So this thing really goes to 2x over 12x, or 1/6. So if our sequence was 2n minus 7 over 12n plus 4, that would approach 1/6 as n got really, really large. So eventually, when n got big, all the values would be really super close to 1/6 and just getting closer and closer. Well, we've got this one. So we know, what does this do? As n gets really, really big, it goes to 1/6. So then, what does this do? As n gets really, really big. Well, if the inside's going to just essentially be 1/6, then the whole thing is going to essentially be ln of 1/6 in the end. That's it. So you just really have to see that inside the parentheses is just a kind of a precalculus problem. What's the limit as x gets really big of that function, 2x minus 7 over 12x plus 4? Yeah?
I just want to know if you're recording.
I am recording. Yes, thank you. I never mind the reminder, okay? Because sometimes I forget, so thank you. All right, let's go on to the new stuff. So one more thing about sequences we didn't get to. I want to talk about something called factorial. Let's see. Okay, so just before we start, what's a sequence versus a series? What's a sequence? So all this stuff is meaningless if you don't know this one first basic thing. A sequence is what, and a series is what? Other way around. The sequence is a list of numbers. It's a list. And we're talking about infinite sequences, ones that go on forever. And then the series is when we take everything in the list and we add them all together. Okay? So we got to have that basic fact down. We have no stumbling over that. Okay? When things get crazy and there's rules and algebra flying around, sometimes just that basic fact can help you make sense of the problem and make progress on it, okay? So never lose sight of that. Okay, so factorials are like this. Factorial is denoted by exclamation point, okay? Okay, so this is not 4, right? So this means 4 times 3 times 2 times 1. What it means is you start with a number. You start with a number, and then you multiply down. You subtract 1 every time. You subtract down whenever. It's the best reaction ever. Okay? So you start with 4, and then times 3, and then times 2, and then times 1. Okay? So 4 factorial is the same as 24. Okay? Just so you know, 0 factorial is defined as 1. Just so you know. Sometimes that comes up. It's not 0, it's 1. And why that is a whole different story. So just take my word for it. Okay? So how about 6 factorial? What's 6 factorial? Well, it's going to be 6 times 5 times 4 times 3 times 2 times 1. So that's how it works. So what is it? 70? 720. 6 times, let's see, that's 10, 4. So yeah, 720. Good. All right. So then, if you had something like this, maybe. No, you don't have to get your calculator out. You just have to think about what's going on here. So if it's 28 factorial divided by 25 factorial, let's write out, okay, is it 3 factorial? So let's just start writing out what 28 factorial is, okay? We won't write the whole thing. You can thank me later. Here's how we can write out 28 factorial. And what do you notice about 28 factorial? Exactly. It has a tail. It includes 25 factorial. It's right included in it. Do you see that? So if we were to take 28 factorial and then divide by 25 factorial, what would be left? Just the first. So without working this out, you might think, oh, 3 factorial. Well, no, it's much different than 3 factorial, right? But at least, I mean, that's thinking along the right lines. We just got to work it out. So really, this ratio, 28 factorial divided by 25 factorial, is 28 times 27 times 26, whatever that is. So yes, you need a calculator for that. Did you get it, Matt?
Yeah, it's 19,650.
19,656? Okay. Okay, so then let's look at a sequence, right? So what would this sequence be? So let's write the first three terms of the sequence and then determine if it converges or not. Can you do it? I'll start taking roll. Work together. What'd you get for the first three terms? The first term is 1/6. Second term. What is it? 1/6 over 120. And then? Over what? Yeah, good thing we only did 3. Everyone good on the first 3 terms of this? Make sense how you do that? Okay, so here's what we want to do. Now we want to simplify this. And so what's it looking like it's doing here? It's going to get small. Okay, so we're thinking maybe this goes to 0. So let's prove it. So what we're going to do is we're going to write out what is 2n minus 1 factorial. You're just going to start with what? 2n minus 1. And then next is? Which is right. So it goes down by 1, right? So you start with that number and you multiply and you go down by 1 each time. Next one is 2n minus, and how far do we go? 2 to 1. It's always to 1. Always, the last 3 will always be 3 times 2 times 1. No matter where n is, you just keep going until you get down to 1. That's what factorial means. So this one will be, start with 2n plus 1, then next, down by 1, and then, now look what's going to happen. The next thing's going to be 2n minus 1 all the way down to 1. What's that? Basically, what's left here is 2n minus 1 factorial. Do you see that? So once we get to 2n minus 1 and we're doing factorial, well, then we're just going to go down to 1. Well, that's exactly what we have in the numerator. So then this thing right here, the rest of 2n plus 1 factorial, cancels out with the whole numerator. And in the end, we have 1 over 4n squared plus, that's fine. Yeah, let's do that. That's great. 4n squared plus 2n. So an is the same, that sequence I gave you is the same as this sequence. 1 over 4n squared plus 2n, because we multiply down to 2n minus 1 factorial, to 2n plus 1 factorial, and then simplified. So this is the same as that. And that clearly approaches 0 as n gets large. Which is what we suspected by looking at the first 3 terms. Okay, but this is an important skill right here, to see an expression in a factorial and be able to write what that expression means. Question, yeah?
Why are you changing it from -1 to -2, -3?
Because of what factorial is. You start with it. So 4 factorial starts with 4, and then multiplies what? 1 less. And then multiplies 1 less.
But isn't that what n is?
No, so n is, so for a given n, so like the 6th term in the sequence, right? So if when n equals 6, then what do we have? We have 2 times 6 minus 1 factorial over 2 times 6 plus 1 factorial. So what is that? That's 11 factorial over 13 factorial.
Yeah.
So we could work out, so what is that? That's 1 over 13 times 12. Well, that's just for n equals 6. That's just the one term, n equals 6. So that's what I'm doing here. Just for any given n, this is what 2n minus 1 factorial is. For that same n, this is what 2n plus 1 factorial is. Is it better?
Yeah.
Okay. Other questions? Okay, so those are gonna turn up, so we just gotta get used to working with those. But yeah, writing it. So writing this out. This is maybe the most important step of what we did, because you need to understand factorial that way and be able to write it when it's given as an expression like that. Okay, so now we're ready to talk about series, which is really what the whole chapter is about. Sequences are just laying the groundwork for talking about series. So let's just remind ourselves again here. Let's make fancy Nancy fill. Okay, so this is the important thing, the important fact that we have to hold on to when we're in this whole entire chapter. Sequence is the list. The series is the sum of the numbers in the sequence. Okay? So, and we use, to write a sum, we use this symbol like this right here. That means sum. And we did that before, right? At the beginning of the semester when we were doing the, working up to our integral. So we were summing up a bunch of little bits of a quantity, right? So we've seen that before. So therefore, if given a sequence, a sub n, the associated series is the sum of the terms of the sequence. And it's going to start at 1. And then we're going to work with infinite series. Infinite series means just n keeps going and going and going, and we just keep adding the terms together. So can you write out what that means? So when I write those symbols right there, sum of the sequence a sub n when n starts at 1 and gets infinitely large, what does it mean? What does it mean to do? What do we start with? A1 plus. Okay, some people are listening. And how far do we go? Just keep going. So we're going to see a lot of these, and whenever you see one of these, you think this, okay? Whenever you see this, you have to think this. That's what that thing is symbolizing, okay? That's really, really important. Okay, so the first sequence that we did was 2n minus 1. So, therefore, so can you write out what that means? Write out what that sum means. It means what is it going to take the terms of the sequence and add them all up. So what's first? 1. When n is 1, this is 1. What's next? 3. Then? Yeah, this was the sequence of odd numbers, right? This was our sequence of odd numbers. And so the series means to add up all the odd numbers. And what's going to happen when we do that? Yeah, that's just going to get super big, right? Because these even the sequence is getting big, and then we're adding them all together. So it's like doubly big, right? So not only are the numbers that we're adding going to get infinitely large, but then we're adding them all together. Okay, so this is what's called a divergent series. So one way a series can be divergent is if its sum goes to infinity, okay? So if its sum goes to infinity or negative infinity, then that's one way the series could be divergent. Okay, another example. 1 over 2 to the n. So you can use the, I could have put bn here or 1 over 2 to the n because they're the same. I'll just do it that way this time. Okay, so see this, think what? Go. See this, think what? Write it out. Okay, first term of the sequence, or series. What is it? 1/2. Then? Then? Okay, so let's think about this. This is like, suppose, I don't know, a turtle's on one side of the room. I don't know, it's the first thing that came to mind. Here's a turtle, okay? And so here he is at 0. And say this is 1. Or 1 whatever. I don't know how wide this room is, but okay. So first he goes 1/2, right? He goes 1/2 and he's here. And then he goes 1/4. So we're going to add that on, right? So we're going to add on 1/4. So he's going to end up here at where? 3/4, right? So this is 1/2 plus 1/4 is 3/4. Then he's going to go 1/8. He's going to end up where? 7/8. Then he's going to add a 16th. Where's it going to be then? 15/16. So we're just going to keep adding on like this forever. Does he get to the other side of the room or not? Okay, if he ever stops, he'll never get there. But if he just keeps going, he'll get there. But he can never stop. Okay? So this is the idea. So this, when you sum up all the terms from n equals 1 to infinity, equals what? 1. So this is a convergent series. Converges to 1. When you add up all the terms, you get 1. But if you don't add up all the terms, you won't get 1. Any questions on that? So this is, again, when you see things like this, you have to be able to write this out and think of it this way, because that's what it is. Again, we're going to get into formulas and algebra and doing all these things, and you're going to get your head buried into these expressions like this. You can't forget what it is that it means. Okay, so let's talk about a geometric series. So the geometric series is a series of this form. Okay, what does it mean? Write it out. See this? Think what? See this? Think what? Write it out. So A and R are just numbers. We don't know what they are. Okay, so they represent any numbers, A and R. Okay, first term. Lee, what's the first term of the series? Yeah. And what's that? A. A times 1 is A, right? What's the next one? AR. Yep. This is what you should have gotten. Okay, this is called a geometric series. So the question is, when does it converge? Is that going to be a matter of A or of R? Why is it not a matter of A? Well, R is going to stay the same too. R is constant.
A isn't being
What could we do with the A in this sum? Yeah, there's an A in every term, so we could actually just factor it out, and it could be A times the sum of all these R's. And so then, no matter how big or small A is, it's really going to be up to whether the sum of the R's converges, because then we'll just multiply by this finite number. We still get a finite number, or we won't. So yes, you're right. So what we're asking is for what values of R? Okay, so let's figure that out. Here we go. So we're going to let S n be the sum of the first n terms. Okay, this is called a partial, so it's called a partial sum. Only up to the first n terms. So what is Sn then? Sn is A plus AR. Same thing as before, but we're not just going to keep going now. We're only going to go up to, so if it's the first n terms, what's the last term then? AR to the n? N minus 1, right? Oh, did I miss one? Sorry, I screwed up here. Sorry. I didn't have AR. Sorry about that. Okay, now I got it. Okay, and then here's what we're going to do. So I'm going to multiply that by R. So when I multiply it by R, this is when I'm going to get AR plus AR squared. So my first term now is going to be AR. And then AR squared, then AR cubed. And then I'm going to have AR to the n minus 1, but then I'm going to have one more, right? AR to the n. Sorry, there should be dot, dot, dot in here. What did I do? I just took that one above and I multiplied every term by r. So, but then to get that corresponding term, you'd have to go down diagonally, right? So I multiplied by r, then I multiplied by r, then I multiplied by r. So then the last term, AR to the n minus 1, gets multiplied by r as AR to the n. Why do you do that? Because it works. So what we're going to do now is we're going to, I've lined them all up, so we're going to subtract. So Sn minus Rsn equals, so all these are going to go away, right? Everything in the middle goes away. All we're left with is A minus AR to the n. What's that? No, I subtracted. So I subtracted. So A minus 0 is A, but then all these go away in the middle, and then I have this, I'm subtracting this, right?
I was wondering where AR comes from, like a chunk right
Because we multiplied all these terms by r. So when you multiply this by r, you get AR to the n. So when you multiply this one by r, you get that one. You see it now? Yeah. Okay. And so now if I factor out Sn, so Sn times 1 minus r equals that. And so Sn equals A minus AR to the n over 1 minus r. Okay, so I'm going to break this up into two fractions. A over 1 minus r and minus so what happens is this is the sequence of partial sums. So when n gets really, really large, we're saying for what values of r we need this to go to 0. So if this goes to 0, then this becomes the sum of all the terms, right? So as n goes to infinity, for what values of r does this thing, the second term, goes to 0? Well, certainly r is equal to 0, but this, so do you remember this was one of our special forms of sequences? R to the n. For what values of r did that go to 0? Do you remember? Did we call it p to the n? Did we say p to the n? Is that what we said? Yeah, so we called it p to the n. When does the p to the n sequence go to 0? When r is between -1 and 1. I think that was was that in the video? Or did we do that? We did that in class. Yeah, we got that. We did that in class. The p to the n sequence. So if r is between -1 and 1, that thing goes to 0, and the sum of all the terms is a over 1 minus r. So as n gets really big, this sequence of partial sums, because this fades away to 0 if r is between -1 and 1. And that was our original question. We asked, for what values of r does the geometric series converge? It converges when r is between -1 and 1. And then, as a bonus, we found out what it converges to. It converges, the sum is a over 1 minus r. Okay, any questions on that? Anybody, did you follow that? All that? So let's go back to the one we did right before this, and let's look at it. Can I erase? A over 1 minus r. Can I erase? So we looked at this one. 1 over 2 to the n. So, what about it? What do you notice? What do you notice about 1 over 2 to the n? So we only have geometric series so far, so the only question we can ask is it a geometric series or not? Yes. What is A and what is R? 1 times what to the n? Yeah, so we could rewrite 1 over 2 to the n as 1/2 to the n. That's the same thing, because 1 to the n is 1. So 1 over 2 to the n is the same as 1/2 to the n. So we have a geometric series with A equals 1 and R equals 1/2. Convergent or not? Convergent because we're inside this the interval from -1 to 1. So this tells us that it's convergent. And we also know what that sum is. The sum equals 1 over, remember, we found that it was A over 1 minus R, so 1 minus 1/2, okay? What is, something's not right here. Oh, there's something, so something else, hold on. Okay, we got ahead of ourselves. Hold on. This is not geometric series form. What's wrong with that? N minus 1. Okay, so start over here. Okay, so we need something times something. So it's the 1/2 to the n minus 1, and then it's in the geometric series form. Okay. So what did I just do by doing 1/2 to the n minus 1? How does that compare to 1/2 to the n? So what does an exponent mean? So what does this 1/2 to the n means what? What does that mean? Right, 1/2 times itself n times. N of those. So then what's 1/2 to the n minus 1? How does it compare to this? 1 less. 1 less. So in order, if we need it to be 1/2 to the n minus 1, but we want this to be equal to this, then how can we make this be equal to this? We have 1 less 1/2 multiplied together. Multiplied by 1/2. Then we'll have n of them, right? So if I have n minus 1, and I multiply by 1 more, I have n of them. Did you catch it? So there's n of them multiplied together. I need n minus 1, so all I do is just take 1 out and make it separate, right? Make it separate. 1/2 times 1/2 to the n minus 1 is just the same as n of those multiplied together. Now what's our A and what's our R?
1/2.
A is 1/2 and R is?
1/2.
All right, that's better. Now that's better. Did you catch that trick? That's really important because you have to do that for some problems. It's geometric. If n starts at 1, then that exponent has to be n minus 1. So this is convergent still because R is between negative 1 and 1, and this equals a over 1 minus r, which is 1/2 over, which is 1/2 over 1/2, which equals?
1.
Does the turtle make it to the wall? Yes, if he keeps going. That's the same. That was the same as the turtle problem, right? We got 1. We said 1/2 plus a 4th plus a 8th plus a 16th equals 1, as long as the turtle keeps going forever. Okay, and that's what this found. This we just showed it by this formula as well. Yeah.
Shouldn't it be -1 since it's 1 minus 1 out?
What are you minusing? There's nothing minusing here.
1 minus a half.
Are you good? Okay. It's not. Oh, so you thought you were thinking 1/2 minus 1?
Yeah.
Yeah. Okay. So this just verifies that same problem we did in a different way, right? Different way now. So using geometric series. Okay, let's do something more complicated. Any questions? Okay, here's one. Okay, so the only thing we got to work with now is geometric series. That's all we really know. And so the first question we ask is it geometric, or can we rewrite it in geometric form? So here's the key. It's got numbers raised to the n. Numbers raised to the n is our signal that, yes, it's geometric, right? Because geometric is ar to the n. So we've got things raised to the n. It's just, now it's more complicated than before. So what we need in the end is ar to the n minus 1. So can we transform this so that it's ar to the n minus 1? Well, go for it. I'll finish 10x. So what do we have to do in the numerator? Take one, what? Take a negative 3 out, so we get negative 3 times. All right, that's good. And then 5 is fine. Do we need to take a 4 out? No, it's already n minus 1. So we're one step away. Negative 3/5 times what? Negative 3/4 to the minus 1. There it is, ar to the n. Is it convergent? Yes. So what will happen, what will be different about this series that we haven't seen yet? So if we were to write out the terms, what's going to happen in this one that we haven't seen yet? Switch signs. It's going to be alternating series, right? Alternating series. When the ends are what? Odd. When it's odd, this will be positive because that'll be even, and then it'll be negative, right? So when it's odd, we'll get negative, and when it's even, then that'll be negative, and times the negative will be positive. So as n switches, it'll go positive, negative, positive, negative. But r is still in our interval, right? R has to be between negative 1 and 1, and we're good there. So it converges, and it converges to what? A over 1 minus r. A is negative 3/5. R is negative 3/4. So 1 minus negative 3/4. And if you do the math, you should get negative 12 over 35. So positive, negative, positive, negative, positive, negative, but add them all together, and you get negative 12 35ths for that. Okay, any questions on that one? Doesn't make sense. And when will the geometric series diverge? Yeah, when r is greater than 1 or less than -1. Okay, so let's talk about the harmonic series. Wow. Ugh, it's awful. Oh, that's what we want. That's nicer. Okay. All right, so the harmonic series is this one. Is it geometric? Is it geometric? In a geometric series, where is the n? It's the exponent. So this is not geometric. Okay? You got to have something to the n. That's geometric. This is 1 over n. Okay? So practice. See this? Think what? Go. See this? Think what? Okay. What is it? See. Jet, what is it? Did you get it?
But it's like 1 over 1.
1 over 1. Yeah, just do it.
1 half
Yeah.
plus 1/3 plus.
Yeah, that's what I was asking. That's all I'm asking.
Oh, okay.
Just think what, right? See that? Think what? Okay, so what about, so it's not geometric, so what about just the sequence 1 over n? So, convergent or divergent? Converges to 0 as n gets really big, right? Okay, we know this, right? Because it's basically the same as the function 1 over x. Function 1 over x looks like this. As x gets big, it gets very close to 0. Right? For large x, essentially 0. So same thing for this sequence then is just the points at the whole numbers, and it's going to do the exact same thing the function does for large x. Okay. So now the question is, what about this? What about this series? So we're going to add these together. Is it going to converge or not? What do you think?
Yes.
Okay, we have a yes. So let's here's what we're going to do. So we're going to write out.
So if the sequence converges, is there like a rule?
No. All I asked is if you think the series converges or not. That's all I asked. So we're going to take a closer look at that. So here is this. Okay, so I got 1 plus 1/2 plus 1/3 plus 1/4. I've written out all the terms to 1/9, and then somewhere down the road it's going to be 1/16, and then it's just going to keep going. Okay? Now what I'm going to do is I'm going to compare this sum. So we're going to compare this sum to this sum. So compared to this. Ready? 1 plus 1/2 plus 2 1/4 added together plus 4 1/8 added together plus 8 1/16 added together. So I'll just write those the same way I wrote it above, and so on. So what am I doing here? Okay, so this is 1/2, and now the next 2 terms is what? 1/2, and the next 4 terms is 1/2, and the next 8 terms is. So, do you see that the way I've written the second series, is that convergent or divergent? That second series. I can always get enough terms to add another 1/2. Do you see that? I'll never run out of terms. All I have to do is take twice as many as I took before, and it'll add another 1/2. And I'll never run out. So I can just this just keeps adding a 1/2, eventually just keeps adding a 1/2 and a 1/2 forever. And how does this one compare to ours? Is this one greater or less than ours? Greater? Look, how does 1/3, what's bigger, 1/3 or 1/4? Think about pizza and you'll get it right. You want 1/3 of a pizza or 1/4 of a pizza? It's more, right? This is bigger. What about all these? 1/5, 1/6, 1/7. All bigger than 1/8. 1/9 through 1/15. All bigger than 1/16. So ours is what compared to this one? Larger. Larger. This, the harmonic series, is larger than one you told me is what? Divergent. It's infinitely large. The harmonic series is bigger than one that you could write as just adding 1/2 forever. Therefore, harmonic series, divergent. The harmonic series is divergent. The harmonic series is larger than an infinitely large series. Thus, divergent. Pretty cool proof, huh? Okay, so notice something. The sequence did what? The sequence went to 0, but the series diverged. If the sequence doesn't go to 0, can the series converge? Because what would happen if your sequence, say your sequence approaches 1/2, approaches 3. The sequence approaches 3. Then what? Eventually, you'll just be doing what? You'll just be adding 3 over and over and over again. Is that going to converge? No. So the only chance that a series has to converge is if what about the sequence? It has to approach 0. So in the end, you're adding infinitely small amount. But is that sufficient? This example, this sequence goes to 0. But it's still diverged. Okay? So the sequence has to go to 0 for the series to converge, but that's not enough. It has to go to 0. We've seen this before. Fast enough. It's the same. It's got the same principle as an improper integral. Okay, so that what I just said in the last minute is really important. So let's summarize it. So this is what's called the divergence theorem. So given some series if the limit as n approaches infinity, an does not equal 0, or an is divergent, then what can we say about the series? It's got to be divergent. The only chance a series has to converge is if the sequence goes to 0. For example, okay, what's happening in this series right here? What do you see about this series that we could make a conclusion about it? Okay, remember that what's the difference? What's the sequence and what's the series? The sequence is the list of numbers. The series is the sum. So look at the sequence. What is the sequence? Goes to what? 1/4 as n goes to infinity. Therefore, this is ... for large n is essentially doing what in the end? 1/4. What? Next? 1/4. Then? Forever. Right? So for very, very large n, this series eventually essentially, it's just adding 1/4 over and over and over again. Why? Because the sequence went to 1/4. The sequence converges to 1/4. So then our series, we just keep adding 1/4. Convergent or divergent? Divergent series, right? Sequence converges to 1/4. So therefore, you're adding 1/4 forever. You're adding 1/4 forever. Series divergent. By the divergence theorem. Because, why? Because the limit of the sequence didn't go to 0. So you just end up adding that non-zero number together forever. And it can't possibly add up to a finite value. This principle is really important that you understand this. Okay? So then the flip side of this theorem is that if your sequence approaches 0, then what's the conclusion? The series has a chance. You're telling me there's a chance. If a sub n goes to 0 as n approaches infinity, then the series may or may not converge. It's necessary but not sufficient. It's necessary but it's not enough. The sequence has to get to 0 fast enough so that when you add up the terms, you get a finite value. The harmonic series, what? What's the harmonic series? 1/n. Sequence goes to 0, but we just showed that you add up all the terms, it does not converge. Okay, a couple more things here. Any questions on the divergence theorem? And then this principle about when series converge. So when does a series converge? If the sequence goes to 0, but that's not enough. That's not enough. Can I erase? Okay, so then there's something called a p-series. P-series are of this form. Is it a geometric series? For geometric series, n has to be exponent. Is it like the harmonic series?
Sometimes.
For what value of p is it the harmonic series? Okay, so the p series, the harmonic series, is a type of p series, p equals 1. Okay? So the p series relates to the harmonic series, but does not relate to geometric series. Okay, so the p series converge. So what about when p equals 1? Does it converge? When p equals 1. No, it's when p equals 1, it's the harmonic series. We show that diverges. So the p series converges when it's just like our improper integrals. We did 1 over x to the p, remember? And when did the integral of 1 over x to the p converge? Greater than 1. Okay, so for instance, that converges. But 1 over n to the 1 does not. Any exponent greater than 1 will make this converge. Okay, so in terms of finding what the sum is when they converge, pretty much the geometric series is the only one that we have for that. So if you want to define the actual sum, you just have to add up enough terms to get a good approximation. Does that make sense? Because they're going to get smaller. The terms are going to get smaller eventually and essentially be 0. So if you ever want a good approximation, then you just remember what it means. What does it mean? It means add 1 over 1 to the 1.001 plus 1 over 2 to the 1.001 plus 1 over 3 to the 1.001, and you just add enough terms until their terms are getting small enough to 0 that you have a good approximation. Does it make sense? So the geometric series is the only one that we've got this formula that we can calculate it exactly. All the rest, we could get an approximation, but we just conclude if it converges or not. Okay? So this converges because p is greater than 1. So then anything, 1 over n to the 4th, 10th, those all converge, okay? It's all converge. Because those are going to get small really fast. Those terms get small really fast. And you're adding 0. Let's see. Do one example. Okay, convergent or divergent? And give all proper reasoning. Here's the first step. Agree with that? I multiplied out the first one. And so then I also just broke this up into two different ones. What if one of them diverges? Yeah, so because these are so different, right? So if one of them would diverge, the whole thing's going to diverge. They both got to converge for this thing to converge, okay? So let's start with this one. Convergent or divergent? Because it's a convergent geometric series. 1/4 is in the interval. Okay, convergent or divergent? Is it a p-series? Not quite, but it's like a p-series, okay? So what we have to see is we compare this to, so we did this earlier with a harmonic. We can compare to the p-series. What p-series would we compare it to? 3 over n squared. How do these terms compare to the terms 3 over n squared? How do all these, by adding 3n in the denominator, how does every one of those terms compare to 3 over n squared? Smaller. And if 3 over n squared is convergent, all of our terms are smaller than that. Then, conclusion? Convergent, right? This is called the comparison test. If you have something that's positive but smaller than something you know is convergent, then that must be convergent too. You can also compare for divergence. We did that before. If you have something that's larger than something you know is divergent, then yours is also divergent. But if you have something smaller than something you know is divergent, you can't conclude anything. Or if you have something larger than something you know is convergent, you can't conclude anything. Make sense? It's got to be smaller than a convergent series, that'll converge, or bigger than a divergent series, that'll diverge. So this converges by comparison to a p-series, and this is a convergent geometric series. Web work for Wednesday.